of the fluids panel is to derive the three major fluids equations, the continuity, momentum, and energy equations. So let's go ahead and start, and I'll make sure to talk you through the problem. So I'll start this problem by dealing with an arbitrary shaped control volume with fluid moving through the control volume. And on the control volume, I have a differential surface ds with some normal vector to that surface, so this is ds. So to derive conservation of mass, the continuity equation, the basic principle is that the rate of accumulation inside the control volume is equal to the net mass flow out of the control volume. And I'm saying net mass flow out, but what I really mean is the out minus n. So the rate of accumulation inside of the control volume can be written as d by dt. And again, I'm deriving the integral form of these equations, d by dt of the volume integral of rho d volume. And we said that that's equal to the net mass flux out of the control volume. So that is actually the surface integral of rho v dotted with ds. So pretty straightforward. Let's go ahead and tweak this equation a little more. So we can bring the d by dt into the integral because the limits of this integration never change because it's a constant control volume. And for the surface integral, we can apply the divergence theorem in order to turn it into a volume integral as well. And then we can combine everything into one large volume integral. And then finally, we can note that in order for this integral to always be equal to 0, the integrand must be equal to 0. So here we've derived both the integral form and the partial differential form of the continuity equation. There's also another way to, if you feel uncomfortable dealing with the arbitrary control volume, we can deal with a cubic control volume and more simply actually get to these conservation equations. But let's come back to this derivation if we have time. For now, let's move on to the conservation of momentum equation. So for the conservation of momentum equation, we will actually use the very same control volume. The conservation of momentum states is just another statement of Newton's second law, F equals ma. But we're actually not going to assume a constant mass, and so the sum of the forces equals dp dt, where p is the momentum. So the sum of the forces equals the change in momentum. So let's deal first with the left-hand side of the equation, the sum of the forces. So what are all the forces acting on the control volume? Well, we would first have the pressure forces. We'll have, let's break the forces into categories. We have surface forces, and we have body forces. For surface forces, we'll deal with those first. Surface forces are pressure and shear stress. So pressure, let's say pressure on a region dV of, a region ds of the outer surface area of the volume. So you have some pressure force dotted with because it's a vector, dotted with ds, and we'll actually want to integrate that over the entire surface area. And let's see, the net, so if it's pressure acting into the surface, it's actually always going to be a negative, right? Because the outer surface normally is pointing out. So that's one surface force. Let's now consider the viscous force. So you'd have some integral over the surface of some tau, a shear stress, acting cross ds. So now we have one surface force, two surface forces. Now let's move to the body forces. So body forces are things like gravity, electromagnetic forces, but we'll just represent all of the body forces per unit volume as little f, and then we'll integrate that along the entire control volume that we're dealing with. So now we've dealt with our entire left-hand side of the equation. Now let's move on to dealing with the right-hand side of the equation, the change in momentum versus time. So in order to get the change in momentum versus time, change in momentum versus time is the rate of momentum accumulation